All right, and then there's chapter 2. All right, and chapter 2 is something called Ohm's law. And Ohm's law actually got formalized by Kirchhoff. Ohm did a whole bunch of experiments that showed some things were working quite well, and he had some, phenomenological equations that describe those things. But then Kirchhoff came through, and he improved that using mathematics and things like that. So he improved them quite a bit. And that didn't help. It made things a little bit easier. And Ohm's law is the thing that you've probably seen before, which is the potential difference, or the EMF, the electromotive force, is equal to the current, the electrons going through your wire, times the resistance of your wire, or your circuit element. Actually, it's your circuit element. We'll talk about real wires a little bit after this today, and then when we talk about circuits, next time we'll start talking about circuits. Then we're going to talk about ideal wires. There's a little bit of a difference in those, and we'll talk about that a little bit then. So this is your electromotive force. Which is the same as your potential difference. This is your resistance. Resist. And this is your current. And this is the current resistance. So that's going to tell us what happens in a conductor. And the conductor has a transfer curve like this. That is, when you apply a voltage, you get some sort of current out. And that gives you a line, a nice linear line that goes through 0, right? And that has a slope of 1 over r, right? Because I is equal to just the opposite here, delta V, your applied potential, over the resistance. Okay. So that's basically how much current you get for a given voltage. So that's what you're allowed to control. You control the voltage, you get a current out, and the slope is 1 over r, the resistance in the wire, or in the circuit element. Very important. This is only for metals. So Ohm's law is for metals only. If you have semiconductors, if you have insulators, if you have semi-metals, maybe, they're all different. Might not be for semi-metals. Semi-metals is a fairly interesting concept. And by semi-interesting means I haven't really studied it. So you want Ohm's law, and this is just saying what I said. The current produced, gotta be careful, produced by a driving potential which we call an electromotive force, is proportional to the force, and inversely proportional to the resistance. And this just might, if you're paying attention, remind you what happens in a in a fluid. If you were to take a big pipe and drop a ball in through some fluid, it will reach a steady velocity, and you'd have a resistance to that motion based on the drag coefficient. So the higher the drag coefficient, the lower that velocity is. Remember, I is equal to lambda v, right? So the velocity is resisted by the resistance in this case, which is produced by a drag-like force inside of the material. And it's a similar idea to a sort of a Newtonian drag, where Newtonian drag says, you know, little things are bumping into other things and that's slowing you down. That's what's happening here. Okay. And we ought to say that because of that, you have the same sort of thing that you had in the ball dropping through the fluid, right? The ball dropping through the fluid reached a terminal velocity. The charge reaches a critical velocity, or has a maximum speed, which we call the drift speed. Which we just talked about last time. So that's what's going on there. So the example here is going to be looking at just a resistor and a battery and stuff like that and trying to figure out how much current is in it. Then the time after that, so the next thing we're going to do is we're going to look at the equation for designing a wire, right? How you get the resistance of a wire based on its physical characteristics. And that example will be the long one that has to do with all the different configurations and things like that, and looking things up, and, you know, this is the potential, so what's the current, and this is the design of the wire, what's the resistance, and then how much energy do you lose, or so no, it's not going to be energy you lose, but it's going to be, which I can look at what the, uh-oh, I didn't finish that problem, so I don't know what I'm going to solve for. Actually, I don't know what I'm going to solve for. I didn't finish that problem yet, but I will finish it by the time it goes up, right? I know.